Hello learners, welcome back to my channel Shraddha's Physics. Today our topic is blackbody radiation. Let us consider any object. This is suppose any object. Some white light is falling on this object. So white light means it consists of several numbers of wavelength, and when it falls on this object, then three things may happen. First of all, it may absorb all possible wavelength, or it may reflect any type of wavelength, or it may transmit, this body may transmit any particular wavelength. I can say that if an body or an object, it reflect particular color, then it appear that color. It means that any particular object, it appears red because this object, it reflects the red color. That is why it seems to be, the color of that object is red. When we heat an object, suppose this is my object, I am heating it by some heat source. This is my heat source. When we heat an object by some heat source, it emits the radiation of different wavelength. So this wavelength range, it may varies from 0 to infinity. So some wavelength amount, it may be maximum, or some type of wavelength it may be less. I am saying that if lambda 1 is the wavelength of the light, it emits maximum radiation, or lambda 2 is any type of wavelength, it emits minimum radiation. So this may be possible when we heat an object. Suppose for example, while heating an iron rod, we see the red color, because the maximum wavelength of the red color, it emits comparison to the other wavelength. That is why it appears to be red. But the question is that when the star, we know the star emits all possible radiation, then how could we measure the temperature of the star? So we cannot use the thermometer to measure the temperature of the star. So how can we measure? So simply we can see that when we are heating this iron rod, it appears to be red. Okay, it appears to be red means this iron rod, it emits every possible wavelength, but it appears red because the maximum possible wavelength, the maximum emission is red color as compared to the other wavelength, we can say that. So similarly, by using this relation, that is the temperature with the color, this relation, we can measure the temperature of the star. Okay. Now we will see the blackbody. So a blackbody is a cavity, it is a cavity in the material that only emits the thermal radiation. The incoming radiation, it is absorbed in the cavity, or we can say that every possible frequency or the wavelength of light will fall on this blackbody, it will absorb, so that it has also the capacity to emit, it also can emit every possible frequencies or every possible wavelengths. Now you can see that this is the graph between the wavelength, this is the wavelength versus the intensity. You can see here, within this shortest wavelength region, in this particular region, you can see that the intensity gradually increases, and at some point it reaches to the maximum value, and after that when the wavelength increases, the intensity gradually decreases and it tends to 0, but not exactly equal to 0. So it means that the radiation is possible for every frequency range or every possible wavelength region. From the classical phenomena, that is when we are using the concept, like we have considered the light has the wave nature, that is in the form of classical physics, like Wien's displacement law or Wien's distribution law or the Rayleigh's law. These laws gives different result with respect to the experimental result. You can see here, this is the experimental curve and this is the Rayleigh's curve. Here you can see that this is the wavelength and this is the intensity. So now you can see that while at the highest wavelength region, you can see that at the highest wavelength region, this Rayleigh's law, it satisfies with the experimental value. But at when this wavelength tends to the lower value at this condition, or you can say that at the ultraviolet region, at this condition, this curve tends to infinity, whereas you can see the experimental value, it is not tends to infinity. That's why the ultraviolet catastrophe occurs, or we can say that this deviation from the experimental data is called the ultraviolet catastrophe. All these experiments are based on the concept of the classical physics, where we have considered that the light has only the wave nature. Later when Planck comes, he gave an idea about that the electromagnetic energy, it cannot be radiated or absorbed in any arbitrary amount, but only in the discrete form, that is called the quantum amount, or that is known as the quanta of energy, or that is the packet of energy we call, that is the quanta of energy or the packet of energy. This energy is nothing but hf, or we simply write it as h nu, where h is the Planck's constant. Planck, on the basis of this quantum theory, he considered that the light has the dual form, that is, it may sometimes behaves like the wave and it sometimes behaves like the particle. This Planck law is able to describe in the longer wavelength region as well as the shorter wavelength region. That is the energy density that we have calculated by using this Planck's law. It is satisfied with the experimental result, that is for the shorter wavelength region as well as the longer wavelength region. You can see here this curve, that is this curve, it satisfies with the experimental result. And also from this Planck's law we can derive Wien's law as well as the Rayleigh's law. You can see the relation for the Wien's law, this is Rayleigh's law, that is the energy density relation with the wavelength, and this is Wien's law for the wavelength, it proportional to your lambda power 5, and this Planck's constant, this is Planck's distribution, energy distribution, it proportional to your lambda power 5, inversely proportional to lambda power 5 into exponential SC by lambda kt minus 1, that is it also varies exponentially. The wavelength, it also varies with the exponentially. So we can say that no classical physical law could have accounted for measure the Blackbody spectra. So Max Planck and other, it had no way of knowing whether the calculation of the number of modes in the cavity or the average energy per mode, that is the kinetic theory, was the problem. So it turned out to be latter. Now we will see the application of the Blackbody radiation. It gave people the ability to calculate the temperature of the distant cosmic bodies. It inspired the new devices such as thermal vision and new types of thermometers. So how did Blackbody radiation, it impacts modern physics? It leads to establish the relations between light intensity, wavelength and the temperature. That is from the Wien's displacement law, Stefan's law, Rayleigh's law, and it leads to the ultraviolet catastrophe, and finally on the basis of the quantum mechanics we will deal with the Planck's radiation law. The failure by the Wien's, Stefan, Rayleigh's, it leads the Planck's to explain, that is the discrete values which best fit to the experimental result, and also Planck derived the quantization of energy, that is E equal to NHF, or this is NH nu. So the implication for what occurring at the atomic level is possible. Ultimately it leads to the birth of the quantum mechanics. So we can say that this Blackbody radiation, when the failure in the classical physics occur, then Planck explain the discrete energy level, that is E equal to NH nu form, where the energy density relation is clearly explained with the wavelength. It means that how the wavelength varies with the energy density, is clearly explained by the Planck. This is all about the blackbody radiation.